Okay, let's go ahead and get started. So today we're going to be plotting graphs of functions by hand. So I'll start today with doing an example so you can sort of see how that goes. And then I'll talk about some general strategies for plotting functions by hand. And then what I'll do is break you up into groups at the board to do some examples on your own. And then the web work for today will be a little bit different because it's kind of hard to, I don't think it's possible to do a web work where you draw a function or anything like that. So the web work for today is going to be like extra practice with optimization problems. So sort of like the fence problem that we did before spring break. Okay, are there any questions? So let's look at this example. So we're gonna look at the curve defined by the equation y equals x to the fourth minus 4x cubed. And we'll discuss this graph with respect to all the things that we know. So increasing, decreasing, local maxima and minima, inflection points, and concavity. And we'll also draw a picture of the graph. So we'll look at the concavity, inflection points, local maxes and mins, and we'll also and increasing, decreasing, and we'll sketch it as well. Okay, so to determine these things, we're gonna need to know the first and second derivative. So I'll just go ahead and start by computing that. So if we set f of x equal to x to the fourth minus 4x cubed, then what is f prime of x gonna be? Yeah. Yeah, good. Yes. So this is 4x cubed minus 12x squared. Okay, looks good. And then what is the second derivative going to be? Yeah. Yeah, that sounds good. So we get f double prime of x is equal to 12x squared minus 24x. And then it's going to be helpful for us to factor both of these. So let's go ahead and do that. So this one, I can pull out 4x squared, and I'm left with x minus 3. And then for this one, I can pull out 12x, and I'm left with x minus 2. Okay, so those are our first and second derivatives. Okay, let's start with the critical numbers. So what are the critical numbers for this? Yeah. 3 and 0. Yeah, so the critical numbers. And how did you get that?
Because the x minus 3, when you equal that to 0, you get 3, and then when you equal the 4x squared to 0, you get 0.
Yeah, so the critical numbers are just wherever f prime of x is equal to 0. And so we get that that's when x is 0 or x is 3. Okay, good. So let's take a look at what the concavity is at these 2 points. Because we want to know the concavity anyways, and then this will also potentially tell us whether these are a local min or max from the second derivative test. So let's look at f double prime at these values. So f double prime of 0, so just plugging 0 in for x here, we get that this is equal to 0. And f double prime of 3, let's see, this is 12 times 3 times 3 minus 2, so this is 36. Okay, so what does the second derivative test tell us about the concavity based on this calculation? I'll maybe start with this one. So at 3, we get that f double prime of 3 is a positive number. So what's the concavity of the function there? Concave up, yeah. And then what about here? So this could be an inflection point. It'll just depend on whether or not the concavity changes at that point. Yeah. So this is like a candidate for an inflection point. Okay, so this is a candidate inflection point. And then this one is we're concave up here. So since this is concave up, yeah.
Okay, so just concave up. Is that like opposite concave? That's there.
Up or down is going to be the determination. So convex, I don't think the word convex is ever used in calculus, but usually math convex refers to like a shape where it has the property where if you pick any 2 points from inside the shape, that the line between them is fully contained inside of it. So like this entire thing is part of my shape. So like, for example, something that's not concave could look like a beam, and then the line segment between the 2 points is not concave there.
Okay, but it's basically so
Yeah. Yeah, exactly, yeah. But yeah, a graph typically won't be like a convex shape because if it's curvy at all, it'll violate this, yeah.
You just know that it's concave if it's positive versus negative.
Yeah.
Okay.
Yeah, so if the second derivative is positive on some interval, then you're concave up, and if you're negative, then it's concave down. Other questions? Okay, so we have here at x equals 3 a point where the derivative is 0 and you're concave up. So you have a horizontal tangent there and you're concave up. So what can we say about x equals 3? So that one is going to be a local minimum, right? So since it had a horizontal tangent, it's a candidate for being the local maximum or minimum. And then concave up tells us that all values of the function around it will be larger. So we get that this is a local minimum. Okay, so for for x equals 0, is this one, or could it be a local max or min? Let's figure that out. So we're looking at the critical numbers and trying to decide what happens there. So let's take a closer look to decide, is this a local max or min? So how could we decide that? The second derivative test didn't give us any answer. Yeah.
Does the second derivative test not give you an answer? Because it won't, like, for it to be a local max or min, so.
Yeah, so is it possible for the second derivative to be 0 and still be a local max or min? I think it is possible. Yeah. Yeah, so how can we check if this is a local max or min using the test that we know? Yeah. Yeah, so the first derivative tests has us looking at obviously the first derivative. So let's use the first derivative test. So the first derivative test has you looking at whether or not the first derivative is changes from positive to negative or negative to positive at that point. So what happens there? So check if f prime of x is positive or negative. On the intervals okay, so we need to check the interval to the left of 0, so negative infinity to 0, and then we also need to check the interval to the right of 0 and up to the next critical number, so that would be the interval from 0 to 3. Yeah, let me make sure f prime is visible. Okay, so this is our f prime. Is this positive or negative for values of x that are less than 0? So is it positive or negative on this interval? Yeah, so it's going to be negative there. So here it's negative. And then what about for values of x coming from 0 to 3? Yeah, so this is also going to be negative. So since it's negative, for both, so the first derivative test tells us if it's going from positive to negative, you have a maximum there, and if it's negative to positive, then you have a minimum, and if it doesn't change sign, then you have nothing there. So since it's negative for both, this is not a local max or min. Okay, so okay, so that was like the critical numbers and whether or not they're maxes or mins. Let's also quickly do whether or not the function is increasing or decreasing on intervals, because we've already checked 2 of them. So for increasing / decreasing, So what does this information tell us? The fact that the first derivative was negative on these two intervals. Yeah, so we know that the function is decreasing on those two intervals, negative infinity to 0 and 0 to 3. And then let's check. So the last interval would be from 3 to infinity. Okay, so let's look at f prime again. So on the interval 3 to infinity, is this positive or negative? Yeah, so this is going to be positive. So we're increasing on this interval. Okay, so now let's look at what we wanted to know about this graph. So we figured out the local maxes and mins and also where it's increasing and decreasing. So let's do the concavity now, and then we'll be able to sketch it. And the inflection points. So let's do inflection points first. Okay, so how do I find the inflection points? Yeah.
Where the second derivative is equal to 0.
Yeah, so let's go, I'm just gonna copy this. These are our inflection point candidates. So where f double prime of x equals 0 is a candidate. Inflection point. Okay, so looking at this, that's going to be when x is either 0 or 2. Okay, and then to determine if it is an inflection point, we just need to see if the concavity changes on either side of those 2 points. So these numbers break the real number line up into intervals where the concavity will be constant on each interval. So we get, so here I'll list the intervals. Negative infinity to 0, 0 to 2, 2 to infinity. Okay, so then let's decide if f double prime is positive or negative on each of those intervals, and then that will tell us the concavity there. Okay, so for values of x from negative infinity to 0, is f double prime positive or negative? Yeah, so it'll be positive, right? Because we're plugging in here, this term will be negative, and this term will also be negative, and so we're multiplying 2 negative numbers, so we get a positive here. So we're concave up on that interval. Okay, and then what about from 0 to 2, what happens? Yeah, so this will be negative because here we're plugging in a positive number, and here this will still be a negative number, and so negative times positive is negative. Oops. So here you're concave down. Okay, and then for the last interval from 2 to infinity, yeah, this is going to be positive. So here you're concave up. Okay, so now we know everything. Oh, right. Okay, so what does that tell us about these 2 points? Yeah.
Tell me absolute max.
So what this says that these are just both inflection points because that's where because we do actually see, for example, the interval to the left and to the right of 0, you have a different concavity there. So it changes from positive to negative or negative to positive. So this is our last. Okay, so x equals 0 and x equals 2 are both inflection points. Okay, so now we know a lot of information about this function. So let's draw a sketch of how it looks using this. Okay, so the important things were we have x equals 0 and x equals 2 are inflection points. And we also had that x equals 3 was a local min. And then okay, so yeah, let's use this to start sketching the function. So I'll just draw some axes. Okay, so here was 0, 1, 2, and 3. Okay, so 3 is our local min. So it'll be useful to know what is f of 3. And I've forgotten what f was, so let me go back to the beginning. So f was x to the 4th minus 4x cubed. Okay, so what is f of 3? This is 3 to the 4th minus 4 times 3 cubed. So I'll pull out 3 cubed. And this leaves us with 3 minus 4. So this is negative 27. Okay, so this is not to scale, so I'll put negative 27 down here. Okay, so this was a local min. And we also know that on the interval from 2 to infinity, we are concave up. So can draw something like this. So from 2 to infinity, I'm concave up. So over here, I'll look something like that. And then at x equals 2, we have an inflection point. So I'll also compute f of 2 and plot that number. So this is going to be 2 to the 4th minus 4 times 2 cubed. Forget. 2 cubed times 2 minus 4. So this is minus 16. Okay, so it's going to be somewhere like that. Okay, so going this way now, I'm concave up until I get to x equals 2 and then concave down. So it looks something, so here, wait. Okay, so something like that. Are there questions so far? So at x equals 2, we'll switch to being concave down. So it might be useful to know actually what the x-intercepts are. That'll help us figure out, first of all, what that point is. We can actually label it, and then I'll also figure out, as this is heading towards the x-axis, where does it actually hit? So, let me just quickly figure that out. So if I set the f to 0, so 0 is equal to x to the 4th minus 4x cubed. Okay, so let's factor this. So we get x cubed times x minus 4. Okay, so my x-intercepts are at x equals 0 and x equals 4. So okay, so I can go ahead and label this point as well now. So that's 4. And okay, so what that means is I'm gonna be moving to the left from 2. We're gonna be concave down, heading towards 0, which is where the x-intercept is. And there's other stuff going on at x equals 0, right? This is an inflection point. And what else did we know about it? The derivative was 0 right there. So it's going to be something like this. And then, so we're concave down there, and then after that, it's concave up. Okay, so let me. Okay, let's just check quickly that this is like the picture that we've drawn is consistent with all the information that we know. So, with concavity, so we had these 3 intervals, -infinity to 0 is concave up, and that looks good. 0 to 2 was concave down, and that looks good. And then 2 to infinity is concave up, and that also looks good. And then as far as increasing, decreasing, it looks like our picture is decreasing until x equals 3, and then it's increasing after that. Let's just see what we had. Yeah, so we had decreasing from -infinity to 3, and then increasing from 3 to infinity. And we have that one local min there. Okay, are there questions about this? Okay, so what are we doing on time? Okay, let me just summarize some things that you can look at to help you sketch the graph of a function, and then I'll break you up into groups to get some practice with it. So things to consider. When sketching graphs. So often the first thing you want to do is check the domain of the function to see if there's anywhere where it's not going to be defined. Because if it's undefined somewhere, then something interesting is going to be going on for values close to that. So check the domain. Another thing you can look at is the x-intercepts. So that was helpful in drawing our picture. You can also look at the y-intercepts. One thing that we didn't do in this example, but can be helpful is to know the sort of tail behavior. So what is the limit as x goes to infinity or negative infinity of that function? So the tail behavior the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x. So this information will just help you in your picture determine what is going on to the left and the right of your graph. Okay, and then there may be vertical asymptotes. Or rather, I'll just say like, so if you have numbers that are not in the domain of the function. So for example, it's a rational function and you have some value that makes the denominator 0. You're going to want to compute the limit to the left and the right of that denominator so that you can see what is happening as you get close to that value. So for numbers a, where the function is not defined, you want the limit as x approaches a from the right of f of x and the limit as x approaches a from the left of f of x. Okay, and then the things that we have been doing, so you want to know where it's increasing and decreasing. You want to know the critical numbers. And then from there, whether there's a local max or min in any of those numbers. And then you also want to find the concavity and inflection points. So it'll depend on the function that you have, whether or not you need to do various ones of these. So for example, if you have a polynomial, you will not have to look at places where the function is not defined. For example, or like in our case, the tail behavior was pretty easy to just deduce from the other information that we knew about the function. But these are just some things you can check to help you draw a picture. Okay, so I'm gonna break you into groups and give you some graphs to draw, and then when you're done, I can plot it on my computer and we can check your picture. So let's have this first row. You guys will come to this board. The second row will come to this board. The third row will come to this board, and the last row will come to this board, and I'll come around and give you a function.